Hi guys! What's up? Anyone was at Maki last night?
This guy.
Oh shit, I'm the only one. Okay, cool. Yeah, so I'm gonna talk about interactive proof systems. How many of you heard of ZK, zero knowledge proofs? Okay, so I'm probably gonna like go through like the intuition on how ZK even became a thing. So it really comes from this concept of interactive proofs, and I'll also like maybe talk about how this relates to the project I'm working on. So I'm not gonna shill too much. I'm going to be more educational in this talk. Yeah, so I'm going to give a quick intro to like this concept of interactive proof systems, which is really the basis of zero knowledge proofs, and talk about how this actually relates to ZK SNUCs, and also like further optimizations like polynomial commitments, arithmetization, and also like zero knowledge machine learning, which is what we are essentially doing. But we don't necessarily always use ZK. So we kind of only want like the verifiability aspect most of the time. And if there's time, I'll show like the demos and some of the experiments that we have done. Okay, so why is verifiable computing matters? Why do you even want to verify things at all? So the problem is that there's a lot of bullshit in the world. So if you're going to Token 2049, you're probably going to hear a lot of bullshit. So like someone will be launching like, hey, buy my cat coin, buy my dog coin, and then like there's meme coins and shit. So you don't really want to bother with this kind of things, and you kind of want to filter out bullshit. And so how can you actually model this kind of like bullshit in general? And so there are many kind of risky and low trust environments in the world. Think of like things like smart contracts, war, and also but yeah, it seems like schizophrenic mathematicians are the ones who came up with this idea. So yeah. So the guy who came up with this concept of interactive proof systems is, I can't pronounce his name. They have like so many like Laszlo Babai. So I remember his name as Babai. Yeah, but basically it came from this concept of Arthur games, and they use like the concept of graph isomorphisms and coin tosses. But we're gonna talk about applying it to Southeast Asia. Yeah, you recognize Zundamo and Shikoku Metan? Okay, great. I guess there are a lot of weeds in this place. Okay, so essentially we have two players. Think of it as a game. So you have a prover and a verifier. And so the prover has infinite computational power, but it can't be trusted. And so the verifier is now playing a game where it needs to kind of check whether this prover is not bullshitting them. Okay, so let's contextualize this in C. So you can think of this as a challenge response game. So in Pattaya, so if you go up to someone and say, "Are you a lady boy?" "I'm not lady boy, nah." Okay, so the verifier is like, how can I know for sure? So yeah, really all of ZK can be, or even like interactive proof systems can be modeled as a challenge response game. So think of it as a game, like you have multiple rounds and you kind of want to prove something. And so you can do things like index ring, finger ratio test, body fat percentage test, and period test or whatever. And you can do even more rounds. And so if the prover has enough valid answers after many challenges, you're probably not a ladyboy. Sorry, no hate to my ladyboy friends. Okay. So now we have this concept of challenge and responses. How do we actually formalize this system? Okay, so if you think about like the initial the state of the problem, you can model this as some form of input string. And so in this case, the input string is just like it's kind of a set membership kind of thing, and this would consist of sexual dimorphic traits between male and female Homo sapiens. And you have things like random inputs. So the random inputs are now like the challenges that you essentially issue to the prover, and the prover will basically provide a response to the verifier. And you can model this interaction as a partial message history. So it's just like message 1, message 2, and so on. And so essentially the verifier is a function that takes 3 variables. So the sigma, a symbol that is used in computational complexity, represents like the concept of an alphabet. So it's all the things that you can use to represent things in this game. And so at the end of like this process of providing the challenges and responses, you either accept or reject the answer. And this is essentially the formulation for the verifier function. And now we have to model the prover. And so the prover basically takes in two things. It has an input string, a partial message history, and also the message that it's going to send to the verifier. So so now we can define the interaction between the prover and the verifier, where essentially if it's even, so if you have 2 rounds, it means like it's a verifier's turn. So if it's 1 round, it's the prover's turn. And so it basically keeps alternating as many rounds as needed until you get like the right answer. And so in this case, the number of messages exchanged here are at most a polynomial length Pn. So it's a finite polynomial length. Okay, I'll stop here just to check whether you guys are like conscious or like not sleeping. So so in this formulation over here, do you notice that we don't encode reject? Why is that the case? Anyone want to provide an answer?
Assume that reject is the default.
Not exactly. But yeah, that's also one way of like putting it. But yeah, it's kind of tied to Pn because you have a finite amount of length. It will eventually terminate at some point. So it's not like a Turing machine where if it's not halting, like it's basically the answer is false. So okay, so in order to get a valid answer, you kind of have to repeat the rounds many times. And so you kind of want to do it as many times as possible to know for certain whether the prover is legit or crooked. So in computational complexity, we only deal with like 2 out of 3, but in practice, we kind of need it to be quite certain. Okay, so I don't think I can have enough time to cover these bonus questions, but there's this thing called like the PCP theorem, as well as and so this concept of interactive proof systems and this complexity class called IP. And an exercise here to show that NP is proof within contained within IP itself. Okay, so now let's go into succinct zero-knowledge proofs. So how does this concept of challenge and response actually goes into this concept of like ZK snugs? So I think people probably have talked a lot of ZK snugs a lot, but they have actually not talked about the intuition on why this is even possible. So also in practice, we have been building a lot of ZK stuff in the blockchain space for the past few years. And it seems that zero knowledge is not always necessary. So sometimes you don't exactly need things to be private. So for example, in like L2s, most of the time you're not really using the zero knowledge property, but mostly like the succinctness of ZKPs. And which is why ZK rollups are actually not a good representation of the name, because you're not actually really having any ZK properties at all. And so we also found out that the concept of non-interactivity is really useful. And so I'll talk about how this non-interactivity is even possible at all. So ZK snugs are indeed a special case of the IP complexity class, or interactive proof systems. So the issue with like the many challenge and response games that we were playing just now was that interactive proofs are very interactive, and so that's actually not a good thing if you're trying to do anything online. So if you played any game or some kind of MOBA like Dota 2, does anyone play Dota over here, or am I the only one? Okay, yes, there's one person who plays Dota. Okay, so the issue is that once someone goes AFK, like the whole thing goes to hell, correct? And so if you have like many rounds for a proof system, like it's going to be a pain in the ass to get the actual proof. And so Adi Shamir and I think Amos Fiat came up with this heuristic. And so the idea on how you make this interactive system non-interactive is that you have 2 assumptions. You have to assume that a random numerical function exists, and you have one-way functions. So in practice, this is actually not true. We'll see why this might potentially have some issues. But the idea in this case is to replace the challenges from the verifier with the hash function. So you can model the hash function as like a random oracle in this case. And so the hash function then encodes like the challenge and responses. And so remember like the random challenge R, and the input string which models like the problem that you're trying to solve, like graph isomorphism, so on, and the partial message history. You can essentially now model this whole thing as a single step process with a hash function. And so the verifier function that you see just now is now compressed to a single hash, which is very neat, provided the one-way function exists. So yeah, if you want more details, I left like links in my slide. So I'll send my slide somewhere, and you guys can view the references later on. So this is the catch, and so it turns out I think there was like a paper published last year called "How to Prove False Statements and Practical Attacks on Fiat Shamir." So Fiat Shamir is not guaranteed to be safe, and it's also because if you're using hash function like SHA-256, or even things like Poseidon, which is typically used in ZK, they are not exactly one way or deterministic. So you can show that there's a collision. It's kind of over. So I think this is also an open question for the Poseidon hash function, which is used a lot in ZK. We don't actually know what is the cost to kind of find a collision in it. And also hash functions are not truly random. And so depending on the construction you have, you can potentially find essentially two proofs that verifies to the same witness value. But for most cases, like it's practical enough for use cases. And okay, so this is about the PCP stuff. This related to the bonus question. I'll pass on this thing. Okay, so now we have the concept of ZK snugs. It's kind of really hard to express any kind of mathematical expression as ZK snugs, and it's still kind of useless right now. So at this point, we are essentially back in 2010. So it took us almost like 10 years. So when I was like a kid until now. So I heard about ZK snugs, and now it's actually practical. It's kind of insane. So there are a few things that are still missing. So we need things like arithmetization. So arithmetization is the process of turning a mathematical expression like 1 + 1 or a + b into a form that's suitable for like the ZK circuits. And also, like the concept of PCP or probabilistic checkable proofs are still not very practical in practice. So they tend to have very large proof sizes, and also they take quite a while to generate. And so recently, people came up with the concept of polynomial commitment scheme. So it's in a way a relaxation, and this is what is being used in practice. So have any one of you participated in a KZG ceremony of Ethereum? Okay, only one person, another person there. Amazing. Okay. So yeah, so KZG is an example of a polynomial commitment scheme that's used for blobs right now on Ethereum. So this is kind of practical, but really it's built on 4 algorithms. And so the first phase is the setup phase, and essentially the ceremony does this process. And that's where you get the public params, where everyone knows about it, and you can use it to create a commitment and proof, and then use it to verify. So 4 steps: setup, commit, proof, verify. And this is basically the gist of all the kinds of polynomial commitment scheme that exists. But where KZG is one of like a very common one. So Scroll actually has a very good blog post about this. I suggest that you read this if you are interested in this. But I'll roughly go through like the maths. Yeah, and so essentially you have like a generator function, and so this is the setup phase for Ethereum. You're essentially producing like many degrees of this generator function, and you have this value t, which is tau, which is a secret value. And so this is kind of like the random strings that you generate in the KZG ceremony, and you discard. You pass it to someone, generate, and discard. And so if everyone discards it, like you can't really find like the value of t. So I think the security factor is 1 out of n. If at least one person discards it, like t would be secret. And next, yeah. So this is basically like the commitment phase. So you essentially produce, let's say you have this polynomial function phi. You essentially run the generator on top of phi to produce this commitment. And then you have another evaluation like phi A equals B. You can then generate a proof on that with the same generator function. Yeah, and essentially the verify process, it boils down to this. You're essentially verifying a bilinear mapping in a polynomial space. I shan't go through the details about this because I think it's probably another like math course. But essentially, like you have 4 steps. And now you can essentially verify information using polynomials. So the next other thing, which is also quite fascinating, is that now you have this concept of KZG. You have essentially like many polynomial equations. And so now you have this concept of arithmetization. So let's say I have a function like a plus b, and I want to encode this polynomial. Like, how do we do this? So Plonk introduced this concept of like it stands for a really long name. I can't remember what it was. But the idea is that you can essentially represent like generic mathematical equations in this form, where you have essentially switches, inputs, and also constant terms. And so you can view this basically as a circuit. And so that's how the circuit looks like. So you have like constant terms, and so your constants in the circuits are public values, and your x in this in this setup are essentially private values, and the s symbols over here represents switches. So you can think of it as electrical circuits. Which is why like the concept of arithmetic circuits are being used. Like they call it circuits. And so now with something like this, you can essentially express the concept of addition. For example, if you want to do like a plus b or L plus r equals 0, you essentially just put 1, 0 on x and r, and put 0 on the constant, and you essentially get the concept of 0. And so because it's in this form, you can essentially put it in your ZK, your polynomial-based ZK circuit quite easily. And so you have the concept of multiplication, and also you can simply assign constant to this form. And here's where it gets interesting. You can also do things like non-linearities like ReLU functions. So for example, you want to express the concept of max 0 and x, you can do something like this, where you essentially you can use like the right switch and essentially allow any kind of input to go via like XR in this case. And so now you have the concept of addition, multiplication, and nonlinearities. You kind of have like a basic block of a neural network. And so this is essentially like the basis of like the project that I'm doing called Ezekiel. And so now with the concept of Plonkish arithmetization and polynomial commitment schemes, you're now able to express like neural networks. So this is kind of handy. So if you want to write a neural network, you can essentially use things like TensorFlow or PyTorch and convert into this like format called ONNX. And so we are heavily reliant on ONNX to produce ZKPs. So instead of writing like your circuits in like things like Circom or a specialized language, you can essentially use AI or like the same AI programs that you use, which is kind of handy because you don't need to think about the ZK elements in this case. You just think of it as math. And so you can kind of think of ZKPs in this case as a way of increasing the compute expressivity of the blockchain. So consider if you have like smart contracts, you have like gas limits, you have, there are some things that you can't really do. Let's say if you have like very weird operations or even like exponentials on the blockchain, it's kind of hard to do that. Or even like summation. Summation is and finding averages. So you can do like a time-weighted average sequence, but then it requires like additional cost. So with like the concept of ZKPs, you have the idea of like computing something off-chain, putting it on-chain, which is the basis of ZK as compression. And so it's kind of a really handy tool for how you can increase what blockchains can actually do. In particular, Ethereum right now, because we mostly built it on ETH. So I'll go through like a demo to kind of make this kind of concrete. So I have about 3 minutes left. So I ran this previously, but essentially Yeah, so for example, I have a neural network defined as such. Like if you can see, a model is essentially like a sequence of linear layers, and you have like a forward pass in this format. You can essentially train it, and you can then ZK the neural network by calling this library called Ezekiel, which is the library that we built. And so back to like the 3 steps, so you have setup. So in this case, we split it up into 3 steps, like get SRS, compile circuit, and setup. But essentially, they are the same setup steps in the polynomial commitment scheme. And you can then run proof and verify. And so all the complicated like mathematical stuff that you would have to deal with is now encapsulated in this program and abstracted from you. And so the cool part about this is that you now get this generated Halo 2 verifier. So in the past, you would have to write this by hand. If you wrote something in Circom, you would still have to write the verifier by hand. So we basically built a tool to kind of generate like the verification function on Solidity directly. And all you need to do is call verify proof. And that's it. And it makes it really easy to think about the business logic of how you can use ZK on-chain versus the technicalities of ZK. Yeah, I'll go through some interesting examples. I don't think I have time to go through all the experiments. Yeah, but there's one experiment that's like live right now. So it started as my hackathon project at ETH Denver. It's called CockSwap. It stands for Cleverly Optimized and Computed Swaps at ETH Denver. Oh yeah, it was like Singapore first, and then I did at ETH Denver, like on Balancer instead. So you can think of this. So we are working very closely with Balancer right now. And so you can think of it as like AMM's on-chain on steroids. There are a bunch of things which are possible, but right now we are focused specifically on dynamic fees on-chain. So I think one interesting use case for ZK right now is you have many static parameters on-chain, and you might want to change it. So you can go via a DAO, but that's sometimes too slow. Like trying to get people to sign things on-chain is kind of hard. And so this is where like AI would be really useful. And having the AI be verifiable is even more important. Suppose if you have like a pool that has $200 million in value, you don't want some random AI to be changing stuff. And so we have essentially some incentivized pool. Why is it unincentivized? Yeah, it's incentivized. Oh, wait, it's unincentivized, yes, amazing. Yeah, so we actually have 2 pools that, this is part of the experiments that we did. And so we actually found a class of models which are able to increase the fee collected by LPs. So we can essentially defray impermanent loss on chain right now. So the difference, I think, is it's like roughly about 20%. So on static fees, we are getting around 34%, and on the dynamic fee pool, we are getting like things like 49%. And so we have like a proposal live coming soon. It's actually live on Balancer right now, and so we'll probably be managing the RVE pool and be doing other kind of fund management stuff with like things like Balancer. And so this is kind of like the design space which we are at. You have something on-chain that you want to change, something that might be static, and you want to make it dynamic. This is where things like ZK and verifiable AI is really very useful for at the moment. And there's quite a lot of value that I think is still unlockable, because there's so many things that are static simply because it's troublesome to change on the smart contract. Yeah, I'll basically end here. And so this is the Discord, and if you want to contact me, I'm Henlo Jseam on TG and on X. Yeah, this is, I think, like way too fast, so sorry if I went too quickly. Any questions? Hello.
Thanks for fantastic sharing, and I want to ask, like, based on like in the interactive ecosystem, so the final result of the system is based on like the result of each round, right? So how is there any specific like measurement or metrics that you can prove that, oh, it's enough, it's the times of the round that is sufficient to prove the result?
Oh yeah, so I think there are some examples, right? So So the example that they use is called a public coin. It's like a public coin flip. So for example, I want to know whether the coin is biased or not biased. So let's say it's truly random. I basically ask the guys to keep flipping the coin, and if it's like close to 50%, like it means like the coin is fair. Otherwise, it's not fair. So if, yeah, so the bias coin example is probably like the best way. So if I flip it once, if it's heads, I still do not know. If I flip it second time, it's tails, maybe 50-50, but I still do not know for sure. So I keep flipping many more times until I get like a fair indication that it's like 50-50 after like maybe 1,000 rounds. Okay.
So I guess you're talking about upgradable contracts, right? So you're talking about putting in the AI to replace a DAO. So in the case of like a Tally DAO, you have like a proxy event pattern. What does the pattern look like when an AI is controlling?
So it's not exactly like completely upgradable. So in this case, we are specifically dealing with parameters. So the AIs that we are doing in this case are not LLMs. So LLMs tend to be quite vulnerable. So we have actually, so I think there were people talking about trying to snuck large language models, but we found them to be quite impractical and also like vulnerable to attacks.
Pretty hard to build a CK model around.
It's actually doable at the moment. So we are able to snuck GPT-2, and I think it's possible to snuck GPT-3. But I think the question is, how do you prevent like hallucination attacks or like prompt injection, which tends to happen. And if there's like $200 million of value and you have like a prompt injectable like LLM that is controlling it, that's disastrous. So we are mostly dealing with smaller models, like think of things like decision trees or even things like logistic regression based models where the behavior is understandable. And so yes, using those things to change specific values. So it's very similar to what something like Gauntlet does. So I'm not sure anyone here use DeFi or knows of Gauntlet or Chaos Labs. So they're essentially like involved with calculating things like LTV parameters on Aave. So for example, on Aave, like how do you decide that the LTV should be 75%? So people like Gauntlet will create data science models to say that 75% is probably good for this like pool, and then through governance, they will just set the value on Aave through a DAO vote.
For liquidity debt?
Liquidity debt, in what sense?
So that when you liquidate your position, you can liquidate it correctly without too much slippage.
Yeah, I guess like finding like the optimal liquidation point is also important. So there's essentially a lot of this kind of parameters on chain that it might be good if they can be automated. So right now it's just like a value that is fixed, like for example 75%. It's typically more conservative, and so they do not change this like for years. So which is kind of a great business. You just do the work once and you charge like the protocol $1 million and you just like fuck off. It's kind of a great business to do. But in this case, like if you want to squeeze in more value, like this is having some kind of keeper function that calculates the value based on some kind of protocol data is kind of important. I hope I answered the question, or if I'm not clear, like let me know.
Is it possible to put an agent in it to automate the thing?
Agent in what sense? So I guess like in this way, like the fee managers, you can consider it as an agent, but not a very smart one. So its main job is just to figure out what are the best fees. If no other questions, feel free to just ping me and I'll share the slides. So I think I left a bunch of like papers and maths, which kind of go through the story of like interactive proofs and ZK in a more concise fashion, because I feel like most references are kind of overwhelming, and so I feel like people do not really like have the time to read through all of these things. So I